And meteors attacking us. Okay, we are falling. And we are falling into a black hole. Can we get off to the side? Okay, well this is a new way to die. Did we just go back in time again? Yeah, looks like it. So, it seems today we aren't doing a new episode of Astrophysicist Plays Outer Wilds. We seem to have gone back in time to the previous video, so we can talk about the physics of it. Well, let's go ahead and talk then. This is a new series I'd like to call Astrophysicist Talks, or alternatively, Astrophysicist Draws on a Whiteboard. Now, I'll warn you in advance, this is going to include a whole bunch of me sketching things out using my mouse to draw on the whiteboard here, so things might go a bit slowly, and if it feels that way to you, I recommend speeding the video up to 1.5x or double speed, whatever feels comfortable for you once we get into things. So, let's go back to the footage. As we see here, we are falling into a black hole. Or, if you watch the episode, we narrowly evade falling into a black hole on this occasion, but then later fall into the black hole. So, what I want you to look at here is not the black hole itself. It's a black hole in space. That's pretty obvious. I want you to look at what's going on around here, just outside the black hole. Space seems to be stretched and smeared out, and this is actually amazing that the developers put it in. I'd be very interested in knowing how they programmed it, because this can be very computationally intensive. This is a phenomenon known as gravitational lensing. So, what's going on with gravitational lensing? Let's say we have a black hole. Draw it like this. Now let's imagine that we have rays of light passing beside it. Let's start out a ray of light way out here, going beside it. Now, if it's far enough away from the black hole, it's not going to feel much effect from the black hole's gravity. But as it gets closer, once it starts getting near the black hole, it's going to be attracted to it and will kind of follow a curved path until it eventually goes off straight, and then intermediate paths will travel less, and as we get closer, they'll travel more, even looping around the black hole, almost as if they're orbiting it. And at some point, even at the point that it can act somewhat like a mirror, with rays of light wrapping all around it. But why is this? Why does light do this near a black hole? Well, let's imagine we don't have light at all. Let's imagine we just have... let's imagine we just have a physical projectile going by. So, let's think about how gravity affects it. At every point, it's being pulled towards whatever has this. The amount it's pulled towards is related to the inverse square of the distance if we're just doing Newtonian gravity. So when it's very far out, it doesn't feel much. When it gets closer, it feels a little bit and is attracted to it, but keeps its own velocity. It keeps being attracted, and eventually it gets past the point where it was maximally attracted and starts going back again, and eventually it would go around and do a big loop. I've kind of drawn it off the screen, but if it were on the screen, it might look something like that. Now, in Newtonian gravity, there are basically three ways something could be attracted to a central object. The first way is that it barely interacts with it at all, and in this case, it follows essentially a giant parabola in space, where it's just slightly bent, but it comes in, just going off into the distance, and goes off. Actually, sorry, scratch that. It's a hyperbola here, not a parabola. There is a parabolic option, but in the most extreme case, it's hyperbola. As it gets closer, it it takes a parabolic path, but things have to be lined up exactly. In more generic cases, when it's coming in and gets attracted, it could get trapped, basically, and go into an elliptical orbit. If it's aligned just right, it can be a perfectly circular orbit. And if it happens to be headed straight at the object, it'll collide and do something with it. Things are pretty similar with the black hole for a physical object, but the angles that it comes out do end up being a bit different, particularly as we get close to it. And we don't really collide with the black hole, we fall into the event horizon. So let's think about light. What happens when light goes near a black hole? Does it bend like an object? Well, let's think about it. So historically, people thought that light was a particle and would act like that. So hypothetically, if light was a particle, we would see the same sorts of actions. It would be bent if it's far away. It could go into orbit. Or alternatively, we could imagine light from near the black hole going up, and then it's slowly drained of speed, and then it falls back down. But light isn't a particle. Light is a wave. And importantly, light always travels at the same velocity, or the same speed, with the magnitude of velocity always equaling a constant we call c, the speed of light, a ridiculously fast amount that was very hard to measure, but eventually we could measure it, and later even found that light always travels at the same speed. So it doesn't make sense to think of light going up, slowing down, and coming back. It does make sense to think of it turning, but one of the things that happens with physical objects is that when they're in a big elliptical orbit, they don't travel at the same speed. When they're very close to the center, they travel very quickly, and when they're further out, they travel more slowly. This can be thought of in a way as conservation of energy. When they're close to the object, they're at a very low potential, and so that energy goes into their kinetic energy. They travel faster. When they're farther away, they're at a higher potential, and they travel more slowly. But light can't speed up or slow down. So does it make sense for it to be slow down like this, or even travel in a path like this? What's going on? Well, people were thinking about this for a while, and they kind of gave up on the issue, didn't pay it much mind because it wasn't really interesting. Before light was conceived of as a particle, they actually thought through, like, what if a star was massive enough that any light coming off of it would fall right back down? They call this a dark star. So back in the classical, let's say we have a huge, massive star so that any light from the surface, well, let's imagine that any particle traveling at the speed of light from the surface would be pulled back down before it could escape, even if it's traveling at the speed of light. In this idea, somebody looking at it from over here, imagine I'm drawing something resembling an eye, would look at this, but none of the light rays would get out, and so you wouldn't see this star at all. So they thought of this as a dark star, and they even went and calculated how massive would it have to be. And it turns out, or you can also reformulate it, what radius would it have to have, and the calculation comes out to be radius equals 2 times the gravitational constant, this is basically just describes how strong gravity is in the universe, times the mass of the object, divided by the speed of light squared. So if the entire mass of the object fits within this radius, then you've got something that light maybe couldn't escape from if light was acting like a particle. This is often known as a classical black hole, but since light doesn't work this way, it's unclear how things would actually happen. And for a long while, it wasn't clear. People basically shrugged and said, huh, that's odd, and soldiered on, working on other interesting problems. It wasn't until much, much later, I'm talking like over a century or two later, that people started looking at this problem again. And it came about in discussing Albert Einstein's theory of relativity, which basically, here's the standard cartoon everyone does. Let's imagine that we have a standard grid of space. Now, let's imagine that we introduce mass to it. Mass distorts both space and time around it, stretching it out. So instead of things being straight, imagine I do this straight, they would be like attracted to the mass and compressed in. And if instead we had a bigger mass here, things would be more distorted. Anything else that's going by this always travels along what it sees as the flattest path and straightest path through space. That is, something over here isn't going to be taking any unnecessary turns. So we have a particle here where space is flat and grid-like. It wants to stay along that grid. And when it sees the grid starts to turn, it wants to stay along the grid, so it stays as well. And it follows a path which leads us into the mass here. Since in this case, this is a pretty extreme distortion I've drawn and would suck things into it. And also, I forgot to draw, but the ones on the side would have been dragged in as well. And this formulation of gravity means that things work in the local limit that, just the regime that you and I work with every day. It tends to follow the same laws as Newton's theory of gravity. The same equations work just fine in that limit, but things start breaking down when they get very extreme. And so while people were puzzling out how to do this at the extreme limit, it was noted that once you get very close to the center of a mass, the equations for the field go a bit wonky. And particularly, they go wonky where the distance from a point mass is equal to 2 times the gravitational constant times the mass divided by c squared, which by a big coincidence is actually the radius calculated previously for the classical black hole. So even though the physics was wrong there, it ended up predicting the radius where things go wonky in the general relativity formulation as well. So let's talk about exactly how things go wrong in the general relativity formation. So first, let's do some diagrams of space and time. So let's put up two axes here for time and distance. And let's say this line is the speed of light between them. So if you start out at the origin, you always go forward in time. You can just wait, go forward without changing position. You can also move, but you can't move faster than the speed of light. So the slope is limited here. You can try to get up to that speed, but you can't quite reach it. You can go back, you can speed up, slow down, and follow some sort of path. Now, once you start going closer to a black hole, then the axes start to distort a bit. Rather than being vertical as we had before, you can think of the axes as kind of getting compressed together, at least relative to what we see from the outside. So for somebody getting close to a black hole, it would start to look more like this. Their options get more and more limited, where the black hole is off in this direction. So you can think about this, if you just wait the path of not moving position, you're naturally going to get closer to that black hole. And then as you get even closer to it, your options get more limited still, until eventually, when you reach that magic radius, the two axes overlap. Both the time and the x-axis are the same. You are inevitably crossing that event horizon. This is what's called a singularity, where time and space basically collide on each other. But it turns out this is only from the perspective of someone outside the black hole. Someone falling into a black hole will always see this. Their time and space will always be perpendicular, however close they get to the black hole. And this seems weird, doesn't it? Why would we see two different things? Well, let me go to a different example here. Let's say we have a long, thin ribbon. And you can think of this as having like axis space here, time here. And then imagine we have a race of small people who live on this ribbon and experience a two-dimensional world. So let's say here that they have, X and Y coordinates for their world. X going this way, Y going this way. They describe their place in terms of X and Y. They understand Y is limited up and down, but X is unlimited. Now, imagine some god comes in and twists the ribbon. So instead of looking like this, it folds over on itself and looks like this. So over here, let's say this side is coming up and this side is going down. You can kind of visualize it. It's hard to draw it with a rough sketch. So on the other side of this, the ribbon is upside down. So let's think back to the perspective of these people and their coordinate system. Over here, you've got plus X and plus Y, and plus X will always be to the right. Plus Y over here is always up. But then as we get closer to the twist, the plus Y starts shrinking until eventually at this point, the plus Y is just 0. And then past it, the plus Y goes down until it evens out. So as they're trying to describe the coordinates of places, looking at it from this perspective, they see over here, oh, wait, that's a degenerate point. That's a singularity. But it actually isn't. It's just going through a different dimension that those people don't have access to. So let's think about it. Let's say one of them decides to go over and explore there. One of these little guys takes a path and decides to investigate what's going on at this singularity. So from their perspective, let's imagine we're going with the twist. So right along there, they're going to see, oh, the ribbon is still flat here. It still seems to be flat, but looking over, it seems to be twisted on either other side. So yeah, from their perspective, they'll just see the edge of it off to either side of the twist. But right in it, it seems, no, this is stable. Y is always going up. And then if they keep walking further, they'll end up on the opposite side and see that Y is going up again as they followed this twist. So if you rotate your perspective and use a different set of coordinates, the singularity vanishes. Another way to look at this is, let's think about the planet Earth. So let's say we have a sphere here. I'm drawing the equator there. We have a North Pole here and a South Pole. And the position on Earth is always measured with latitude and longitude. Latitude is the distance away from the equator, and longitude is on one of these great circles around it. But you'll notice when measuring longitude, right at the pole, all of the lines of longitude intersect with each other. So if somebody goes to the pole and you ask them, what's your longitude? They won't be able to answer because it's every longitude. And so just because the coordinate system we're using stops working doesn't mean space itself stops working. And this is what happens when we get too close to a black hole. So from an external observer's point of view, time and space start out looking like we're used to. Sorry, that's time, not y. And as they get closer, as you get closer to the black hole, so let's say this is far away, this is close, and this is at the event horizon. The event horizon being the radius where things go wonky. The time and space axes start to overlap, but from the perspective of someone making that trip, in every case, the two axes always look perfectly perpendicular to each other. So from the two different perspectives, something different is happening. This leads to the idea that, maybe somebody could actually fall into a black hole. From an outside perspective, it looks like they're hitting a singularity, but from the perspective of somebody actually doing the following, there doesn't seem to be any difference there. So maybe they could pass through it. Now, there are a few quirks, like one is that the curvature of space changes so rapidly that, well, let's imagine that you have a stick figure human here falling into a black hole. So since the curvature of space changes so rapidly, the force of gravity on their legs is going to be huge, but it's going to be a bit less on the middle of their body and even less on their head. So if you subtract off the difference here, what you end up with is you've got a force up on the head, nothing on the middle, and a force down on the legs. And this means that once you get close enough to a black hole, you'll find yourself being pulled apart. They called this spaghettification because your entire body gets stretched out like a piece of spaghetti. So our human here, their head gets stretched out like this and legs like this as they fall into a black hole and look like the grossest piece of spaghetti in the universe. So it's not entirely safe to go into a black hole, but if you imagine just an individual particle going into that, it's not going to be stretched out like that, and it can make the journey. And in fact, it turns out that as black holes get bigger and bigger, the change in force across the event horizon gets less and less. So for a large enough black hole, a human could survive the trip across the event horizon. So what happens after you pass through a black hole? If you remember our axes, they go from perpendicular to close together to overlapping. Well, it turns out, and here I'll label these for clarity, that after you pass through the black hole, the axes continue in the same manner as they were. And so the position axis was going up. It keeps going up. Time axis was going down. It keeps going down. And then they start spreading apart again. Your two axes, relative remember, this is all relative to what someone outside the black hole sees. Your two axes keep splitting apart again. Basically, this is like a ribbon where the two directions have changed on themselves. So imagine we had a long straight ribbon, and then we caused a bend in it. We folded it over itself so that the two axes flipped. It's basically what we've got going on here. So here, x, let's say we've got x going forward and time going up, and then it would flip. What was up becomes left and right. So we've got time going left and right, and x going up from the perspective of someone outside. But from the perspective of someone on the ribbon, remember, forward along the ribbon is always positive x, and side to side on it is changes in time. If I thought through this in advance, I would have swapped the axis and put time along the ribbon, but I wasn't that thoughtful. But yeah, you can just think of it that way. So basically, that's what happens. This is the event horizon of a black hole. That once you go through it, your two axes are swapped. So what does this mean practically, that your axes are swapped? Well, essentially what ends up happening, so let's imagine we're now inside the event horizon of a black hole, and right here is the center of it, called the singularity. This is the position that we were originally moving towards. So if we're moving towards it, that means that if we just sit and wait, our natural path through space-time will take us there. So essentially, if you imagine our axes as we perceive them, our time axis in the future points to this singularity, that we're going to hit it. So from the perspective of someone outside, when they look at us, they're going to see, okay, they've got an axis of time where space used to be, and space where time used to be, and I drew those in the wrong order compared to how I spoke. Let's just imagine I spoke correctly. So for them, the maximum point in position is the singularity, that eventually, as the space is going to end at the singularity, and we can move, and whatever, and if we do anything to change our position over here, so let's imagine our future is in the singularity. If we move right, we're moving forward in time from their perspective. We move left, we're moving backwards in time from their perspective. So these two paths are the same, we just see different axes. So from their perspective, we can't really move in space. We don't have control over that. Our space is taking us directly to the center, but we can move forward and backward in time. From our perspective, no, that's crazy. We don't have control over time. We're eventually going to hit the singularity, but we can move forward and backward in space in the meantime. So you have a limited amount of time until eventually you come at the singularity. And from the other perspective, no, they see us falling into the singularity. We're hitting it at some point. It's just the path through time looks weird. Now, the outside observer can't actually see this. It turns out that the event horizon kind of presents a wall that, because the future of anything, so let's imagine we're inside the event horizon. Our axis looks like this, and the singularity is in the future, and the event horizon is in the past. Well, we can only go forward in time, and yeah, we're still bound by the speed of light. And so if we want to send out a message, if we send out a message even at the speed of light, that message is just going to go towards the future, and eventually the singularity is really at all points in space in the future, not just at zero. that speed of light is that message going at the speed of light is going to hit the singularity. So nothing we do inside can actually escape the black hole. So they're not going to be able to see all of this weirdness happening, but it is happening, at least according to our current understanding of physics. So that's a bit of a mind blow. So let's just take a moment, relax, and get into even more crazy physics. What if there wasn't a singularity at the center of a black hole? Remember our ribbon? So we had a ribbon which turned over and kept going. So the laws of physics got wonky at one point, but then got back to relatively normal. Or imagine we had our turning ribbon where we invert the two axes for a period of time. So at this point, things aren't sane, but what if later we turn them back? Things get sane again, and even in the same order as before. Is this possible? Could this happen in physics? Surprisingly, the answer is yes. People have gone through Einstein's equations and found that you can actually do this. And for instance, if the point here and the point here are actually... So, like, if this space is not just a ribbon and I'm just cutting it off for illustration purposes, and imagine that it could continue down, we could travel through this wonky space to cut across real space and end up somewhere else. And you've probably heard this referred to as a wormhole. So imagine we had a sheet of space which naturally loops around like this. And let's say that over here we decide we're going to distort space a lot. We cut out a hole in it, and we stretch space down and connect over here and come out. Would that be possible? Can we have space take a shortcut? It turns out yes. It's hard to set something up so a human could go through it, but if you want light to go through it, maybe send a message taking a shortcut through space, that can actually happen. So what we've got here is what's known as a wormhole. And if we go back to the game, we'll see that the game actually has a wormhole in it. I'll fast forward a bit and find the place in the game where I eventually do fall through the black hole. Fasting forward. Okay, don't fast. You can fast if you want to. It's not going to be that long. But do remember to resume eating when the fasting is done. Okay, here we go. I found it. Oh. Yep. I'm getting impatient. Black hole, I guess. There we go. Pew! And we're out. Whoa. And right behind it is a big white hole. Odyssey all of a sudden. Can we, like, check the map? Oh, we can. You are here. We are wherever that is. Okay, Brittle Hull and the ship is way over here, so we're across the solar system from it. Yeah, so we've taken a trip across the solar system in a very small amount of space relative to us. We've basically done what I showed you there. We've gone from one black hole to a white hole, which I'm drawing in yellow here since I'm using a white background. You go into one and you come out of the other. Now, there are ways you can set up wormholes to allow travel in multiple dimensions, but in fact, the actual first wormhole that was calculated to be possible was a one-directional wormhole, kind of like what you see in game. We call this a plug hole. So you can think of it that you've got basically two sheets of space, one up high and one down low. And from one, there's a hole in it. If you enter the hole, you fall down, and you come out the other side, where there's a white hole. So around here, you're always attracted to the hole, and down here, you're always repulsed from it. This, yeah, as I said, it turns out to be possible to exist, but there's one big problem. How does it start existing? How do you create a hole in space? So let's talk that through a bit. So let's say we have space. This is what space looks like in its most fundamental form. If you've been watching my previous episodes, you know that the technical term for this is a time quilt. Sorry, I misspoke. I'm in Scotland here, so the technical Scottish term for it is a time kilt. So, how do you create a hole in it? You have to punch a hole in space, and then you have to connect it up to another hole and then spread that apart. And it turns out this how is basically an unsolved problem that we're not even sure there is a solution for. Now, creating a hole, creating a singularity is solved, but opening it at the other end, so imagine this hole grows bigger and then connects to a separate hole, and then we stretch out space between it. That's a lot of steps which we have no way to know how to do. The only step that we can do is punching the initial hole, but connecting it to something else seems nearly impossible. So let's at least talk about the one step we know, punching a hole. So it turns out the laws of gravity I went over before, that things get funky at a radius equal to 2 times the gravitational constant divided by the speed of light squared. So if you want things to get funky and get this fold over, all you have to do is stuff enough mass inside a sphere of this velocity. This isn't easy to do, but it's possible. And there's a couple of ways to do this. One is that you need to use the force of an exploding star to press things inside. So when a star goes supernova, let me just start drawing again. So let's say we have a big yellow star here, and then it explodes on itself. It's not going to explode only outwards, but also inwards. The explosion is everywhere at once, and this inward pressure will cause the center of it to collapse and get denser, while outer parts of it get thrown off. And when the center part gets denser, it can bypass other forces that would normally keep things from getting too dense. And when it gets this dense, it's going to form one or another type of object depending on just how dense it is. At the first stage, where it's just a bit dense, we get what's called a white dwarf. A white dwarf is a hot star that still has thermal energy to it, keeping it apart, and all of the atoms are roughly intact, and it's just inside it, you just have one atom up against another atom, the two atoms not overlapping each other. And basically what's called degeneracy pressure from the electrons in an atom, not allowing them to occupy the same space. But at a certain point, this degeneracy pressure isn't enough for the electrons to repel each other. So if it gets even more massive, like if you keep adding mass to this, the force increases, and eventually it increases enough that the degeneracy pressure isn't enough to hold it out, and it will collapse. And at that point, electron degeneracy pressure isn't enough to hold it in. The electrons get slammed into the center of atoms, and they combine with all protons there to form neutrons. Pre-existing neutrons are still there, and it ends up that the degeneracy pressure of the neutrons is all that's holding it apart, and you get what's called a neutron star. These are the most dense objects that we have in the universe that don't break space-time. So you could theoretically travel near the surface of a neutron star and travel back. It'll be a lot of gravitational force, but you're not going to get trapped by an event horizon, which doesn't allow passage. However, they're held back by the degeneracy pressure of neutrons, and there's a certain point of mass at which even that isn't enough to keep it apart. And if it passes that, it all collapses into a single point. There's no known force that can keep them about, so all the mass goes together into a point. But this point is surrounded by an event horizon, which you can't get back out of. And this is when you get to a black hole. So the single point at the center, and arguably the event horizon that surround it, are a hole punched through space. And these are all processes that could theoretically be caused to trigger. So if we want to create a hole that you can go into, that's theoretically possible. It's a huge engineering issue, but not physically impossible. Getting out of a hole is the near impossible part, because the holes we created are basically one way in, and we would need to set up something so that instead of just going in and staying there, we can go in and come out somewhere else. We'd have to connect it to somewhere else in space, which means, what do? Do we create two black holes at different points in space and through an extra dimension aim their singularities at each other so they connect and then expand? How do we aim through another dimension, and how do we get them to link up? And basically the answer is we can't. So we can't create a wormhole. But that isn't the same thing as saying wormholes can't exist. There is one physical mechanism through which wormholes could just come into existence. Now, I'm not going to get into all of the details about this, but let's imagine way back when the universe was much smaller, everything's closer together, things are very chaotic, you've just got a lot of things around. When we have something going on that's called quantum foam. So I'll write it up. I recommend you look it up on Wikipedia for more information. And this is something that isn't just theoretical, it's been proven to happen. What happens at the very basic level, even in what we think of as empty space, is things just appear and then things disappear at very small space and time scales. So if we're doing our space and time axes again, what can happen is, see, normally if you have something, it'll start and it'll continue existing until maybe it interacts with something else. But what quantum foam allows is sometimes the base 0 point energy of the universe is enough that something will just pop into existence. Now, it has to obey conservation of momentum, so usually something else will pop into existence alongside of it. You just get a spontaneous pair of things, an electron and a positron, which is the antimatter opposite of an electron, to also obey conservation of charge and conservation of lepton number. Don't worry about the details there. Will both appear at the same time, going in opposite directions. But then, since they have opposite charges, they'll attract each other and pull each other back in, and then annihilate each other. And then the energy that went into their creation goes away, and over a large time scale, conservation of energy is held. We just have this blip where the 0 point energy of the universe transformed into actual particles, but then the particles went away and it's just back to that 0 point energy. Now, this seems very strange, but we've actually experimentally confirmed it. If you want to see how look up what's called the Casimir effect. This is experimental confirmation that, yeah, as ridiculous as it is, the universe does indeed seem to do this. That's Casimir. Okay, so the universe can do pair production. Can it do spontaneous twisting of space? Maybe. So maybe we'll get spontaneous creation of a teeny tiny wormhole. Remember that these are not even microscopic, not even nanoscopic particles. I think you'd have to go with attoscopic to describe it. So you would get a teeny tiny place in space where you have a little wormhole connecting two different spots. Could be spontaneously created out of the quantum foam and then immediately disappear. So it could exist, but we can't really use it. Or could we? There's one more thing I haven't talked about yet, which allows us the thinnest of possible hopes of a traversable wormhole existing in space, and that is inflation. So basically, you know that the universe is expanding. So yeah, let me just sketch axes again. Okay. So, space over time. So basically what happens is that as time goes on, points in space get further and further apart. So if you were like right here and your buddy was over there and you're not moving relative to each other and you just wait, you'll go up just staying at 0, but your buddy will slowly start drifting away. Now, this happens, it's complicated. It's due to the dark energy primarily of space nowadays. What it was in the past is more complicated, but the important thing is that there was a time very early on in the universe's history where we believe the expansion was ridiculously rapid. So if you had points here in just a fraction of a fraction of a fraction of a second, these points get scattered off way off the side of the map. We call this inflation. That there is a point in time at which space got expanded ridiculously rapidly, and points that were very close are now maybe light years apart. So putting this together, what if we had pair production going along, whoops, here's a little teeny tiny wormhole that exists for a moment, and here's its counterpart, Well, they got pair produced out of nowhere, but I'm sure they'll collapse in and destroy each other soon enough, but, oh wait, inflation is happening. This one goes flying off here. This one goes flying off here. Suddenly, the two ends are light years apart. And not only are they apart, but since the mouth of each wormhole also covers space, they're getting larger. So, if we put all this together, maybe, just maybe, you could have a wormhole created from the quantum foam early in the universe, coming out of nothing. It splits apart, and just at that moment, space is expanding rapidly, and that wormhole gets torn apart, and so far apart that it can't collapse back in on itself. They're now so far apart it would take years and years, maybe billions of years, or maybe even never, for the two ends to get back together and collapse. And the way they're connected, the inner part is outside of the inflation universe, so you've got a shortcut between them. So maybe with all of this, we could have an actual wormhole. Now, we can't create it, we just have to be very lucky in finding it, and people have searched a lot for a wormhole like this, but haven't found anything that indicates it does exist. We haven't proven it can't exist, but we haven't found one, and without finding one, it doesn't look like we're going to be able to create one. Now, that being said, in the game here, it is perfectly possible for a wormhole like this to exist because it's a created universe. They created a universe where there exists a wormhole connecting up the space around Brittle Hollow to the space around what they call Whitehole Station here. So just drawing it out, we've got one end of the wormhole on Brittle Hollow. Let me just choose a different color. We'll do that red. And then one end on Whitehole Station. And we've got a path through them, which covers barely any space at all. You fall in one, you come out the other. And you can't go back. It's a plug hole type, so you can only go through one way. And, you know, maybe in the history of this universe, this is one that just happened to exist. It was created early in inflation. It got blown up to the size of a solar system and hasn't yet collapsed on itself. And, you know, maybe since it's a plug hole design, it never will. The plug hole repels anything that gets close. So it's going to provide a force outwards, even though the black hole provides a force inwards. And the result could be that the two ends never really attract each other to get back together. And they haven't ever gotten close enough for it to collapse on its own. So we've got this somewhat stable configuration where you've got one black hole, which provides the gravity force to hold a planet together, and a plug hole over here, which repels anything that happens to fall through the center of it. So, putting it together, yeah, this isn't so insane. We actually could have a wormhole / plug hole like this. Now, surviving the trip through it is a bit of another matter. You know, if we go back in the video a bit, you can see that things are pretty distorted when we're falling into it. If light is being distorted this much, imagine how strong the force difference is on our legs. And I'll just, let it play out, and you can watch the way that light gets, basically any light coming off of us gets wrapped around the wormhole and eventually comes back. There are moments like you can see the jetpack thrusters on the outskirts of the wormhole. It's just very cool effect they've drawn. So I'll just leave you in the video. Let's enjoy falling onto a wormhole a couple more times. We are falling into a black hole. Can we get off to the side? Okay, well, this is a new way to die. Haven't fallen into a black hole before. Oh, we're luckily safe. But nope, now we're fast forwarding, and we're going to go into a wormhole. Well, yes, we don't know it's a wormhole yet, but it is in fact one, and we are going through it. Come on, where are we? There we go. Okay, time to go through a wormhole. Ooh. Okay, and all of a sudden we're outside of it and on the opposite side of the solar system with space twisting around it and everything being repelled by the white hole. Oh. Okay, well, thank you everyone who's watched along with this physics-based episode. I really hope you enjoyed it, and until next time, I've been Bryan Gillis. Thank you for watching this episode of Astrophysicist Talks. Bye-bye. Thank you very much for watching, everyone. If you enjoyed this video, please leave a like, subscribe, and click the bell to be sure you get notifications of new uploads. See you again soon.